Attendees are in listen-only mode.
Hello everyone, my name is John DeBella, Vice President of Marketing and Sales, and on behalf of Simulations Plus, I welcome you to today's webinar, which will focus on the exciting new features and capabilities in GastroPlus 9.5, along with a brief discussion on some interesting work we've been doing with MembranePlus and GastroPlus to capture the effects of lysosomal trapping on the oral absorption of drug molecules. Viera Lukachova, Team Leader, Simulation Technologies, and the GastroPlus Product Manager will be presenting today. An opportunity to ask questions will follow Viera's presentation today. You may either send your question using the questions pane on your control panel, or you may ask your question directly using the hand-raising icon. If you're using a telephone to listen to the call, please be sure to enter the unique audio PIN displayed when you join the call. When you enter your audio PIN, this enables us to unmute your line so that you can be heard. This webinar is being recorded for playback at our website, www.simulations-plus.com. Also, upon request, the presentation slides can be made available and shared with colleagues. It is now my pleasure to turn the presentation over to Viera. Viera?
Thank you, John. Good morning, good afternoon, everyone. Thank you for taking time out of your busy schedules to learn something about the new developments in GastroPlus and what are the new features that are coming up for the long-anticipated version 9.5. As you can see from this brief summary of changes or new features that we've added in this version, the title really says it all. There is something for everyone. We have touched again on many different aspects and parts of the program. I will go briefly through some of these, or through all of these features in a little bit more detail in this presentation. So to start with the additional dosage routes module, we have expanded the offering of built-in physiologies in different routes, in different administration routes. One of the most critical, at least based on the feedback, was expanding the offering of built-in physiologies for the transdermal module, which previously was limited to different regions of the skin in human. Now you will have options for physiologies or built-in physiologies for rat, mouse, as well as different regions of the skin or of the body in mini pig. We've also added new physiologies for the dog and mouse lung for the pulmonary or inhaled administration, in addition to previously available human and rat physiologies. And for ocular module, previously available human and rabbit are expanded by addition of monkey physiology as well. The other developments for this additional dosage routes module is addition of new administration route, intramuscular injection, which as well as expansion of capabilities for previously available subcutaneous injection. For both of these, now you will have an option to do an injection of a solution, both intramuscular as well as subcutaneous, as well as injection of controlled release formulations. Similar to the oral controlled release formulations, even for intramuscular and subcutaneous controlled release formulations, you will need to provide a dissolution or a release profile. We don't have a mechanistic model for in vivo release of the drug from a variety of different formulations, but this capability at least allows you to start exploring some IVIVC options, start looking at whether your in vitro release or dissolution profiles are going to give you expected in vivo performance, or if there are significant differences between the in vitro and in vivo dissolution. And these two administration routes have been linked also to the biologics module. So you do have option to do intramuscular and subcutaneous injection for both small molecules as well as biologics. To access the new intramuscular route, you would go through the same menu item as you are accessing all the other routes. We have a new entry for the intramuscular option. And a fairly simple form comes up where you could define your compound-specific parameters or formulation and compound-specific parameters, the depot volume determining what portion of the muscle tissue would, into what portion of the muscle tissue would the initial injection go, and of course the rest of the muscle tissue would then get the drug from the systemic circulation. You can account for non-specific binding or linear clearance in this dosing compartment. When it comes to the physiology, the program or the module comes with a series of built-in physiologies, and this time we've done a better job in making sure that we are covering both human as well as some of the commonly utilized animal physiologies, so you have a wider offering of built-in physiologies from the very beginning, which come with the description of the muscle tissue at the injection site. So that's short overview of the new changes coming up in the for the additional dosage routes. For the biologics module, we've expanded the capabilities to modeling antibody-drug conjugates. Biologics module, this was our new development or a new module which was first released with version 9.0, was limited or was calibrated to do modeling of monoclonal antibodies. Now we have expanded that capability to model also antibody-drug conjugates. The ADC species, so the antibody-drug conjugates with various drug-to-antibody ratios, could be distributing and clearing by the same mechanisms as an antibody would be clearing. So you would have the pore diffusion through going from the plasma into the extracellular space, fluid phase endocytosis, possibility for FcRn binding, recycling of the ADC or free antibody back into the surface of the cell, either to the plasma or extracellular space, possible target-mediated disposition for the ADC or free antibody. The small molecule could get released through deconjugation process. So you would be defining additional deconjugation rate constants, which basically defines the rate of the small payload molecule falling off of the antibody, and this process would be happening in plasma as well as in the extracellular space. And of course, the small molecule will be released from the conjugate through any process that leads to degradation of the antibody itself. So if the unbound antibody or antibody complex with the small molecule is degrading in the endosomes, the degradation would lead to the release of the small molecule. Similar for target-mediated disposition, the degradation of the antibody itself would lead to the release of the small molecule which was still bound. And the released small molecule will then be distributed and eliminated from the body based on its own PBPK model, based on its own distribution and elimination mechanisms, whether it's metabolism, renal elimination, biliary secretion, and so on. For the different drug-to-antibody ratios, for different loading efficiencies of the payload to the antibodies, we do have two different models where you can model or account for a distribution of these DAR species, where you can tell the program exactly how many or what is the portion of different DAR species in your formulation, or you can model it as a mean DAR species, eliminating or releasing the drug going into the free antibody. The setup is very similar to what you would be used to from setting up metabolites for the small molecules. When you are setting up your antibody or large molecule record, you will have an option to tell the program whether it is just a simple biologic or it's an antibody-drug conjugate. And if you tell the program that the current formulation is actually a conjugate, you will have additional option, additional drop-down, where you will be able to select which of the records or another record in the same database holds the properties of the small molecule that is attached to the antibody. And the program will then be using the properties and PK parameters exactly as defined in that small molecule record to account for the distribution and elimination of the released small molecule after it comes off of the ADC. And for the distribution of the DAR species, again, you have an option to simply define a mean DAR drug-antibody ratio or define the whole distribution of DAR species in your formulation. Next couple of slides are showing some of the validation cases for this model. They've been all presented a few months ago at the last year's National Biotech Conference. This slide is showing two sets of simulations for TDM1 ADC in rat with two different formulations, one which had lower loadings where the average DAR ratio was 1.5, the other one with the higher drug loading on the antibody with the average ratio of 3.1. And the plots, the first plot in each series is showing the total antibody, meaning the free as well as the antibody conjugated with the small molecule in various ratios. And the second and third column are showing the concentration time profiles for individual DAR species. DAR 0 means the free antibody, and the DAR 1 through DAR 7 would be antibodies with different ratios of drug to antibody. And you can see that the model really was able to account for the plasma concentration time profiles of all of these different species. Of course, the simulation will be showing also the pharmacokinetics for the small molecule as it's being detached or released from the ADC molecules. We are not showing any of those in this specific example simply because there were no observed data for the small molecule from these examples, so there was nothing to compare it to. But we have another example from the literature for the anti-5T4 ADC, where the authors reported the observed concentrations for the total antibody, free antibody, as well as the released small molecule after it got released from the ADC. So here we are showing the simulations for the total antibody in blue, free antibody, and the released payload or small molecule. The top two plots are showing the simulations in control mice. I believe these were mice without tumors. So we are only looking at the antibody free and total antibody in the plasma and the concentration of the small molecule in the plasma. And you can see that for both doses, the model accounted nicely for all different species. As well as we've got a couple of simulations in mice with tumors where the payload was distributing into the tumor tissue as well. And here we have the simulation for the total antibody as well as the small molecule in the plasma and in the tumor tissue. And again, we're able to account for the distribution into different tumors. And we'll be happy to send the full posters again. Both of these examples were shown in a poster at the last year's National Biotech Conference. So if you'd like to see more details behind this model and behind the simulations, we'll be happy to send you the posters as well. Continuing on the development in the PBPK model, again, we've added new physiologies. We've expanded the offering of populations. Previously, you had option to create built-in physiologies for American and Japanese subjects. We've now added physiologies for Chinese population. I'm not listing the exact source for the references. It's based on the combination of over 100 articles providing information on body sizes, different tissue sizes, enzymes expression levels, and so on. we would be able to provide a write-up upon request, but we do have the built-in physiologies now based on the literature data for Chinese subjects as well. And of course, we've done some validations for a number of different compounds, mainly eliminated by CYP enzymes. This is showing one of the examples, our favorite compound, Midazolam, comparing the simulation in Caucasian subjects that we are modeling with the American population. And you can see that by accounting for the changes in the physiology and the enzyme and protein expression levels between the Caucasian and Chinese subjects, the model is able to predict higher bioavailability of midazolam in the Chinese population. Something that we've discussed for quite some time again was start offering built-in physiologies for the disease states and for the special populations. And the first one that we started with in version 9.5 is built-in physiologies for hepatic impairment for different stages of liver cirrhosis. So when you are building your physiologies in GastroPlus, if you are using the per module to create a new physiology, you will now have another new option when working with human physiologies to decide whether you want a typical healthy subject or subject with a different degrees of liver cirrhosis. And the built-in physiologies or changes to physiology due to the hepatic impairment is all based on published data. We've used mainly this publication by Johnson from 2010, where they nicely summarized all the systemic changes happening due to liver cirrhosis. So not only the changes in the not only the changes due to liver volume and the enzyme expression levels in the liver, but also looking at the enzyme expression levels and changes of the enzyme of CYP3A4 in the gut, more systemic changes like protein levels, hematocrit, changes in the tissue and blood flows and the cardiac output and so on. And those of you who have attended our advanced DMPK workshops actually went through this example by manually making these modifications. So you know that you were able to do it also in the past by going down the list and manually changing the specific parameters in the physiology to account for the hepatic impairment. Now you will be able to do it within a few seconds by simply selecting the specific physiology and have the program make all those adjustments for you. And these two plots are showing a brief validation on at least one of the compounds, buspirone, where we were able to find a nice set of data and literature showing the PK for buspirone and one of its metabolites in healthy subjects as well as in subjects with the decompensated or the late stage liver cirrhosis. And the model, again, I'm not showing the whole story, but the model was initially developed by looking at the parent and metabolite concentrations across different dose levels in healthy subjects, so to get the baseline model, and then we've used the model to simply switch the physiologies to create a physiology for the Child-Pugh score C or the late-stage liver cirrhosis to predict what would be happening in these decompensated subjects. And you can see we do have some misprediction here. We are slightly under-predicting the parent compound shown in red. We have a little bit of an over-prediction for the metabolite shown in blue. But the main question the physiologists would be able to answer to tell you that in the subjects with the late-stage liver cirrhosis, you would see a significantly higher exposure for the parent compound. I think the Cmax, the observed was nearly 10-fold. We are predicting about 8-fold. That you would see a significant change in the parent compound PK, but without much change in the PK of this 1-pp metabolite. So it would at least give you the answer to the main question: are there going to be significant changes in the PK would we have to worry about any dose adjustments when using this compound in the subjects with the hepatic impairment. This is just a little side note, as we are making these physiologies more complex, creating built-in physiologies for additional scenarios or additional conditions. We've just added a little note here to help you identify what physiology you actually created, to help you very quickly identify what you are working with, what was the gender population that you used, and what was the health state for the subject that you are using. And of course, these new developments are also linked also to the population simulations. So when running population simulations, you will be able to do the simulations also for Chinese subjects, as well as for subjects with different degrees of hepatic impairment. And continuing on the development in the population simulations, we have expanded the links to the more age-related covariates between different physiological parameters and age, gender, and ethnicity of the subject. For those of you who've done PBPK simulations previously or population simulations with PBPK model, you know that for especially tissue sizes and blood flows, you would see the spread distribution, which tells you that that specific parameter would be linked to the age, gender, and the ethnicity of the given subject as it's being generated in the population simulation. But many other parameters, and especially all the intestinal parameters, were still varied independently, just using a simple log normal distribution around the mean value. Right? So even though with single simulations, when you just ran a single simulation in the main GastroPlus, we already had the scaling of the intestinal physiology to different ages and body weights, but we have finally now linked it also to the population simulations. So when you are running population simulations with version 9.5, and this is showing at least one of the parameters, the small intestine length, as it would be generated in this population where I've done 50 subjects ranging from 1 through 25 years old, where the baseline physiology was set to a 10-year-old male. And you will see that with this link through the pair physiology with the PBPK model, you would now get a properly scaled length of the small intestine going from the 1 year old all the way up to adults. While with previous versions, you would be looking more at the random variability around the baseline value, which was the physiology for the 10-year-old male. And this was one of the reasons why we were generally recommending when running the population simulations for pediatric subjects that you should be running these simulations for a fairly narrow range of ages, so running multiple simulations for fairly narrow range of ages where these assumptions would still hold. Now the program will be scaling it more accurately for a wider range of parameters. And another reason why in the past you would have to run these simulations for fairly narrow age ranges was the administration or the dose specification. As you know, GastroPlus is working with the total dose per body, which is easy to do with single simulations where you know what is the body weight or body surface area. You can set up the proper dose for that simulation, but it wasn't possible to do with the population simulations. So now we have expanded the capability of population simulations where you can instruct the program to do the dosing not only as a fixed dose, but you can do dosing in milligrams per kilogram or milligrams per body surface area. The body surface area will be available only for human physiologies when you are using PBPK model, because of course the program needs to be able to calculate the surface area, and the equation that's being used is the Dubois equation, which was really calibrated for human. but the milligram per kilogram dosing will be available also for animal species, or you can use it with both PBPK as well as compartmental PK model. The next set of changes related to PBPK is adjustments to the calculation of tissue fractions unbound. And this is something that actually a number of you have come back to us when exploring the unbound concentrations simulated and comparing them for the tissues and unbound plasma concentration. This is what you would see in version 9 or the previous version. The red curve here is showing the plasma unbound concentration. This is the total plasma concentration. And all of these other colored dashed lines are showing the unbound concentration simulated for individual tissues. And this was all done with perfusion-limited tissue models, so in the steady state you would expect that these would be much closer to each other and would be linked to the plasma concentration, even though they may not be exactly the same as plasma concentration depending on the ionization of the compound, which may be different inside the cell than in plasma, but they really should come up to the same values across different tissues. So we have made adjustments to the FUT calculation, and you will now see the ratios or the comparisons of the plasma and tissue concentrations exactly as you would expect. In this specific plot, again, you see a small difference between all the tissue concentrations, which lump into the same value in the steady state, and the unbound plasma concentration, which is caused by the ionization. I believe I've done this for Midazolam simulation, which would be a moderate base, so there would be slight accumulation of the compound in the intracellular space due to higher ionization at pH 7 than in plasma at pH 7.4. And I can just hear the gasping from many of you thinking about, oh, how horrible my models have been and how I'm going to have to redo all of the models. So to just, it's not as bleak, it's not as bad as it may seem just by looking at these plots. First of all, these would not be affecting the distribution, right? So distribution in your model was always based and still is going to be based on the total tissue plasma partition coefficients. So none of this will be affecting the distribution for perfusion-limited tissues. The permeability-limited tissues, there might be effects for the distribution, but for perfusion-limited tissues, the distribution will not be affected by this change. So for perfusion-limited tissues, this change would be affecting only eliminating organ. And even that, not necessarily in all the cases. When the clearance was defined as a linear intrinsic clearance, the elimination rate was already calculated and still is calculated based on the assumption of the same unbound concentration in plasma and in tissue. So this will not affect the change, or this would not have any effect on your simulated PK in cases when you were using linear clearance. It really is going to be affecting simulations only when you are modeling the clearance via specific enzyme. And in cases where you were fitting Km value, the Km value would be fitted to reflect the concentration. So there might be just a shift in the Km value to account for this difference between the unbound concentrations. So the main effect that you may see is what will the predictions look like when you start working with the in vitro Km values and start doing the predictions for in vivo. That's where you might start seeing the biggest difference in the predictions. And again, to address the other concern about are you going to have to redo all the models that you are in the middle of right now, you won't have to. All of the previous methods are still going to be available. So you will still, the previous setting is available. You will be still able to reproduce your previous simulations, but and give you time to actually switch over to the new model. But for the new simulations, we would recommend that you are using this new FUT calculation, especially, again, especially important for the eliminating organs. And to make things a little bit more straightforward and a little bit more transparent, you will see the selection of the FUT method for each of the tissues separately. Right? And for permeability-limited tissues, you will have a selection of the methods separate for extracellular and for intracellular space. Again, previously there was one selection for the FUT method, so especially with permeability-limited tissues, you'd be always guessing what's being used for extracellular and intracellular space. Now you will be able to select a specific method for your perfusion limited tissues, for extracellular and intracellular space in permeability limited tissues. And the same would apply if you want to use user-defined FUT. Let's say you measured fraction unbound in tissue and you want to use it directly. You will not have to do a dance by switching to a different method. You will simply be able to enter your fraction unbound in tissue for perfusion-limited tissues, or separate fraction unbound intracellular and extracellular for permeability-limited tissues. So the whole process is going to be more transparent and more straightforward to see exactly what's being used in each part of the tissue. And we have also finally added these methods for calculating the KPs and FUTs into the database. So if you've been working with models where you were switching the KP and FUT methods across different records in the database will now remember exactly what method it should be using for each specific entry, for each specific record. So hopefully that will avoid some of the confusion and some of the intricacies of working with the PBPK models in cases where you needed to switch and needed to use method other than the default. And again, some of the validation with, just as always, going back to our favorite compound, Midazolam. That's the one where we studied the validation using the observed properties as well as the in vitro Km Vmax values for prediction. You will see for Midazolam the difference for IV dose is very small. If anything, it actually improved for IV dose with version 9.5 FUT calculation than it was with version 9.0. The difference is a little bit more significant for the PO doses, and again, if we thought that our predictions previously for Midazolam, the pure in vitro in vivo extrapolations were already very good, you will see that with this change in the FUT calculations, they are actually getting even better for the predictions from the in vitro KMV max values. And we have started doing also some of the validations or verifications for the DDI simulations, looked at the Ketoconazole. And again, Ketoconazole is one of those compounds where the FUT difference would be very small. So looking at the previous method versus the new method, the FUTs are, there is very small difference in the FUT. The main change it creates in the Ketoconazole PK is that the concentration is decreasing at the slightly lower rate. In the actually in version 9 was decreasing at the slower rate. Now it's decreasing a little bit faster. But when it comes to effect on DDI, it's not really creating much of an effect. This plot is showing, or this graph is showing the baseline simulations. I should have put the legend here. This is Ketoconazole CP time profile. This would be the Ketoconazole liver unbound concentration, and the purple one is Midazolam CP time profile. So this is the baseline simulation without any DDI. When we incorporated the DDI, the predicted CP time profiles are still very similar, and the predicted effect did not change, at least with the Ketoconazole simulation. But it will take us a while to go through all of the PBPK models that we have in the database of DDI standards and recalibrate or revalidate the models with all the variety of DDI studies that we've done when we were initially calibrating or implementing these models. So within version 9.5, all the models for the DDI standards that are coming in the DDI standards database will still have the FUT method set to the previous calculation that was with version 9.0. And again, the reason is simple. It's taking us a little while to recalibrate or to revalidate all of the models with the new FUT calculation, making sure that not only the PK is still predicted well, but also the DDI effects are still predicted well with those models. So the models in the DDI standards database will not change from the previous version, even though we will add one more model into the database. Switching the topics a little bit, going more to the changes that we've made for the IVIVC and bioequivalence simulations. One of the aspects is we've hopefully made a little bit more user-friendly change in the mechanistic deconvolution. For those of you who have used the IVIVC module with the mechanistic absorption model for the deconvolution, you know that the process of deconvolution consists of fitting single viable or double viable function or in vivo release profile in the form of single viable or double viable function into each of the records or formulations that you are trying to use to build the IVIVC. And in the previous versions, as the model was, as the program was moving from deconvolution across from one record to another record, it brought up a form with the initial estimates. So you would still have to be present to click OK. It still required a user action, user input, as it was moving through different records during the deconvolution process. It is now more automated, where we've added this option to just tell the program, don't bother me with those initial estimates, just figure out the best you can based on the in vitro data and run through all of the records in one run and just tell me at the end what you've got. Don't bother me with any dialog boxes throughout the simulation. So that's exactly what you will be able to do. And these auto initial estimates, the program will be either getting them from the tabulated in vitro dissolution profile, or you can actually save initial estimates, initial viable parameters in the DSD file as well. And in addition to making this more automated process, so the program goes through without you having to be under the computer to keep clicking OK on those initial estimates forms, it will also now save the progress and the deconvolution or optimization results in the output in a log file. So if something happens before it completely finishes or before you are able to come up with the correlation function, you will be able to go back to the log file to see the individual deconvoluted viable functions, single or double viable function for each of the records. So you will have an easier way of maybe reproducing or going back to the deconvolutions if needed. And linked to the IVIVC, we've also simplified or tried to make a little bit more user-friendly the transition going from IVIVC to starting to predict the in vivo dissolution profiles and use them in the main simulation. Again, and I know that many of you went through this whole process during our workshops, where if you've built IVIVC, and now you want to use that IVIVC to predict the in vivo dissolution profile to a new formula for a new formulation, and then use that predicted in vivo dissolution profile for new formulation to use a population bioequivalence trial, you actually had to take your IVIVC equation, take it to Excel or some other program, calculate this in vivo dissolution profile, and enter that in vivo dissolution profile back into GastroPlus, into the CRD file, and possibly set the viable function to it. You will now be able to operate a little bit more easily from the program itself, where the form where you are entering the predicted in vivo dissolution profile is now able to read or now has a tool that can read the IVIVC that you've previously saved. So you still have to go through the process of building and validating your IVIVC. But when you are done, you'll go in the IVIVC form, you'll go through File, Save, and save that created IVIVC in the output file, which the program can read. Now you want to use that IVIVC to predict the performance for a new formulation. So to create the in vivo dissolution profile for this new formulation, you'll go to the record for your new formulation, go to the form when you are entering the in vivo dissolution profile, the CRD profile, and under Tools, you will have an option to launch this automated calculator. It will open up the form that looks very similar, where all you need to do is define what in vitro dissolution profile you want to use. And if you have already created DSD file with in vitro dissolution profile for that record, the program will load it automatically, or you have an option to open any file with in vitro dissolution profile, or simply paste the in vitro dissolution profile into the grid. In here, you will open the IVC file with the previously created and validated in vitro in vivo correlation. And when the program has, when you tell the program these two pieces of information, the two files which contain that information, it will calculate the in vivo dissolution profile for you. It will be shown in the next column of the table, and it will be shown on the plot along with the in vitro dissolution profile. And the in vitro dissolution profile will be always shown in blue, and next to it will be shown the red in vivo dissolution profile, calculated from this blue in vitro profile and your correlation function from the previously created IVIVC. So again, it becomes as simple as just going calculate the CRD, tell the program which file contains your in vitro dissolution profile, which file contains your IVIVC function. The program does the calculation, and when you click OK on this form, it will export the calculated in vivo profile back into your CRD file, and you can save this file for the use in the simulation. So again, few clicks and much faster translation or calculation of the in vivo profile. In some cases, you actually want to use a smoother function in the simulation in form of a vivo function, and you will be able to do that fitting again from the same form, so you won't have to close this form and go into vivo. You will be able to simply click on vivo here, do your fitting. Once you have the vivo parameter, just click OK. The program will export the vivo parameters into the same file, and you will be able to simply save the file, which now contains both your predicted tabulated profile as well as the functional representation of that release profile. So again, with a few clicks, you will be able to operate everything from the same form and won't have to keep going through different menus or even different programs. One more of a small adjustment, which was related to request from GastroPlus user group, giving an option to fit the bile salt solubilization ratio or the affinity of your compound to the bile salt micelles to more than 2 media. Right? The previous versions, you were able to enter the passive and or passive solubility, or at least one of those, to calculate what would be the solubilization ratio or what would be the affinity of your compound to bile salt micelles. We were getting requests that in some cases you may have additional media with yet different pH and different bile salt concentrations, and you would like to have a more robust calculation of the solubilization ratio based on 3 media. So you will now have an option to enter data for additional media where you define what was the pH, bile salt concentration in your specific media, and what was the solubility in that media. Another big modification was expanding the options for saving your simulation results and saving all the input parameters that led to the simulation. So from the options where you are saving either all data or only selected simulation outputs, you will now have option to save it not only as a text file, but also in the form of Excel file. And we have two different options to sort all of the inputs in these Excel files. You can do sorting by module, which means each part of the model, whether it's formulation, whether it's gastrointestinal tract, pharmacokinetics, metabolism, ocular, pulmonary, dermal, whatever pieces of model you had linked in your simulation, each of these parts will have different worksheet on the Excel, in that specific Excel file. And that worksheet will contain both physiological as well as drug-dependent parameters related to that part of the simulation inputs. Or you will have an option to sort it by type, where type we mean formulation, drug-dependent, and physiological parameters. So for input parameters, there will be one worksheet for formulation. There will be another worksheet for drug-dependent parameters, and will contain drug-dependent parameters related to all parts of simulation, or intestinal, or pharmacokinetic, or metabolism, pulmonary, dermal, and so on. All drug-dependent parameters will be on one worksheet. And then all physiological parameters, again, related to all pieces of simulation, gut, PBPK, ocular, dermal, pulmonary, and so on, will be on a separate worksheet. So depending on what is the easier way for you to navigate and find the information that you need, you will have these two options to sort out the data. And in addition to, of course, doing the Excel output, we've also expanded the offerings and or what input parameters are being saved in these files. So the program will now, we went through and made sure that every single entry parameter that you are inputting into the model or that is put into the model by default through the physiology is going to be saved in these files, and that applies to the text files as well. So they will be more complete and all the parameters will now be saved in these output files. This is showing just some of the snapshots from intestinal, showing a couple of snapshot tables from the intestinal physiological parameters. And here it's showing the intestinal drug-dependent parameters. And one thing I wanted to point out here is that we've expanded these offerings to display the parameters which you had no way of getting directly from the interface. Things like solubility. You all know that the program, when it's calculating what would be the in vivo solubility in each intestinal region, the program is accounting for the effect of pH, as well as for the effect of bile salts on the what would be the solubility in each region of the intestine. But we sort of ran out of real estate on different forms in the program. So in the program, we would be showing you only what was the in vivo solubility in one of the regions of the intestine. But these output files will now have the listing of the actual final in vivo solubilities accounting for both pH effect as well as the bile salt concentration in each region of the intestine. So we will be able to see exactly what in vivo solubility was used for every intestinal region. Similar for the paracellular permeability. Again, since the actual paracellular permeability is changing based on the changes in the pore radius and porosity, but again, did not have enough room on the form to show you what would be the permeabilities for each intestinal regions. At least now you will be able to see them in this output file, where you will see exactly what was used. And when it comes to the results, if you use the option to save all results, they will be organized on different worksheets in these Excel files in the same way as they are organized on the select curves when you are plotting them on the new plot window. So that should make it a little bit easier to figure out where to find a specific profile that you are looking for. You would be looking for it on the same tab as you would be looking for it on the tab of the select curves form when you are trying to put it on the plot window. So that summarizes the changes for version 9.5, and I think I have only about 5 minutes to go through the additional topic that we added to discuss lysosomal trapping and the effects on the absorption or the appearance in the systemic circulation. This is something that has started coming up more and more frequently recently, and we've seen it also in your project as well as in some studies that we've been doing, how the lysosomal trapping might be affecting the prediction of the pharmacokinetics. And what we are looking at here is the process that is especially important for lipophilic cationic molecules which have log P high enough to permeate the lysosomal membrane, and then due to the ionization will get trapped because they ionize more at the low lysosomal pH than they would be in the cytosol or in the cell water. So these effects could cause a couple of different effects. One is increasing the volume of distribution as the compound is accumulating in the lysosomes in some tissues. And the other effect that we have seen was that these compounds tend to have a longer Tmax than would be anticipated based on the properties of the compound. And I will show a couple of compounds with simulations like that. And there have been actually some articles showing this kind of explorations from in vitro assays. This one is showing hepatic perfusion experiments with a antipyrine as well as with two bases, atenolol and propranolol, where a little effect on this lysosomal trapping is shown for atenolol because it's a less lipophilic compound, will have more trouble getting into the lysosomes in the first place, but the propranolol, which has the right set of properties, would be affected more, and the lysosomal trapping would be quite significant. Or another experiment which was published based on the KECO2 experiments, where the authors looked at the and these are all showing apical to basolateral permeability. So these curves are showing apical concentrations, basolateral concentrations. And these empty squares with the dashed lines are showing the accumulation of the compound in the cell membranes. And showing that really for propranolol, for the lipophilic base, the accumulation was much higher than it would be for the neutral molecule testosterone or for acid, ibuprofen. And the accumulation in the cell membranes in propranolol was affected by addition of bafilomycin, which modifies the lysosomal pH, so it would increase the lysosomal pH, cause less accumulation of the propranolol in the lysosomes, and subsequently less accumulation in the cells. And as I mentioned, one of the aspects where this is going to cause, where this translates, or what consequences it's going to have in vivo, is a prolonged Tmax. And this is showing a snapshot of properties and some of the PK parameters for adecypramine, which again is a lipophilic, strong base, which by any account, looking at the solubility of the compound throughout the intestine and looking at the permeability, and this was one of the compounds for which actual human jejunal permeability was measured, this should be a BCS class 1 compound. It should have a high solubility, and based on the permeability, it actually is disappearing from the gut lumen quickly, and you would expect a fairly fast appearance in systemic circulation based on the quick disappearance from the gut lumen. And yet this compound is showing Tmax around 6 or 7 hours. And one way to account for, and the lysosomal trapping would nicely explain this discrepancy, this apparent discrepancy between the high permeability of the compound and yet slow appearance in the systemic circulation. Where if we ran the simulation in the enterocytes, with the assuming no binding, no accumulation in the lysosomes in the enterocytes, we would have a fairly high and quick Tmax for the compound. But if we do account for possible lysosomal trapping, which we model by changing the fraction unbound in enterocytes, and for some of these compounds it can go to very low, 1% or even less than 1%. We would be able to nicely account for the shape of the profile as well as matching the Tmax. And by the way, this is the plots that I'm showing here, that's all from a recent publication that's currently in press and should be showing up soon in CPT PSP, discussing exactly these effects of lysosomal trapping for the zipramine and its effect on both the absorption as well as the volume of distribution. So we now know what it could create, and in this case of the zipramine, the fraction unbound in enterocytes was actually fitted to match that Tmax value. Of course, that brings another question. Well, can we account for this before we start doing any in vivo studies? Can we account for this effect and start predicting that effect based on the compound properties? And this is where we started looking into our program, MembranePlus, and the example that I will show is using another compound, methylphenidate, again with a very similar properties, a fairly lipophilic, strong base, which is predicted or is expected to have high permeability, and but might have some lysosomal trapping affecting the rate of appearance in systemic circulation. So what we've done is we would do a simulation in our MembranePlus software, which is looking really at the details of the drug permeating through the cell monolayers. And the monolayer cells, we did incorporate the lysosomal compartment as well. So the program we would be looking not only at how the drug is going in between the cells, how it's going through the cells and possibly accumulating in the membranes, how it might be metabolized in the cells, but it is also looking at how it might be partitioning into the lysosomes and how it could be accumulating there due to the differences in the pH between the cell water and the lysosomal intracellular and the lysosomal pH. And the simulation, as it's such a detailed simulation, we are getting the output or the simulation profiles not only for the apical and basolateral compartments for the donor and the receiver compartment from the assay, but we can also examine the concentrations in different compartments of the cell. So we can look at the cell membranes. This is the cell membrane, this is the lysosomal membrane, at the concentration inside the lysosomes itself, the actual concentration in the cytosol, so in the cell water itself, as well as the total cell concentration. So from this, if we simply look at only the cytosol concentration, which means concentration in the cell water itself, and compare it to the total cell concentration accounting for accumulation in membranes as well as lysosomes, we can start getting estimates for what this fraction unbound in the cells would be. And here we are showing the GastroPlus simulations. Again, this is if we assumed no lysosomal trapping and the fraction unbound in enterocyte being 100%. And again, you can see that we would overpredict the Cmax and have shorter Tmax. But if we take the FU as predicted from MembranePlus and use that as a fraction unbound in enterocytes in GastroPlus simulation, we are getting much more reasonable prediction for the in vivo simulation. Of course, this part is still under investigation, and we are still validating all different models, but some of this initial work is showing a great promise that we may actually be able to start predicting the fraction unbound in enterocytes, at least for this compound, for these types of compounds where the trapping in the lysosomal compartment is the dominant effect. And that wraps up the presentation. I might have gone a little bit long, but I hope that there is still a little bit of time to answer some questions. Before we get to those, I'd like to acknowledge the rest of the simulation technologies group, a group of great scientists who are all contributing to the development of GastroPlus as well as MembranePlus and our other softwares, as well as, of course, Mike Bolger, our chief scientist, who is providing great feedback and suggestions, especially when it comes to the scientific aspects of the softwares, and all our other groups at the Simulations Plus. And now I'll be happy to entertain some questions if we still have a few minutes to.
Wow, Viera, that was very impressive as you covered the very, very nice set of features that are coming up in GastroPlus 9.5. I think we will stay online now for the next 15 to 20 minutes because not only did you cover everything that we needed to cover, but there's also now a very nice long list of questions that people have. So we'll do our best to address everybody's questions here within the next 15 to 20 minutes. And we'll start with some questions about the population simulator changes that were made and maybe some upcoming changes in future versions. One question here is about the combination of a patient's race in a population. So is there any way to set up a population where you've got a mixture of subjects, let's say American and Asian populations or subjects in a population group?
No, that part has not changed yet, and I forgot to mention that you still would have to select a specific population and you would have to select a specific health status. You cannot do a mixture of populations where you would have a certain percent of American, Chinese, Japanese, or a general population where you would have a mix of healthy and disease subjects. So you would have to select one of these and you would have to run a separate simulation for each of these populations and health status.
Okay, thank you. Since we're on the topic of the hepatic impairment, any thoughts on including renal impairment population groups?
Yes, a lot of thoughts. It would be the next disease on our list to tackle, looking at the renal impairment. So far, we've done some of the validation simulations mainly for renally excreted compounds. And the cases that we've done, typically we were able to account for the changes in the PK by simply modifying the either GFR or the transporter expression levels depending on what was the actual secretion mechanism. But we will need to do, it will take more time to incorporate the renal one, especially how it might be affecting also metabolism. Because we do need to do a lot of literature search to compile all that information. With the liver cirrhosis, it was a little bit simpler because some other groups already have done the work and compiled all the systemic information. So it was a little bit simpler to find the changes. With the renal, I'm not aware of a publication that would summarize it yet, so we will actually have to go through all the publications and create the summary of all the physiological changes to get that done. Okay. But it definitely is on our list. It will just take a little while longer.
Okay, thank you. Is the percent binding in the enterocytes parameter included in the population simulations and sensitivity analysis in GastroPlus 9.5?
Yes, it is in both, and I'm pretty sure it was included in sensitivity analysis already in version 9. I can't remember if it was in population simulation. I know the only limitation was that we didn't have it in optimization, so it was manual optimization. But it certainly will be included in both sensitivity and the population simulation.
Okay, thank you. In the population simulations, the default values for the percent CVs of 10% is assigned to most physiological parameters. Can you comment on the justification of using this value, and have you seen any references on using maybe a slightly higher percentage? 30% seems to be more typical for some of those.
The problem is that we have that for many of those parameters we really did not have good information physiological information. We were able to find the information on the variabilities for, let's say, tissue sizes, and those are included as realistic values. We've had information on intestinal pH, and we've had that information included, and surprisingly, actually, those are coming only about 10 to 15%, so those don't seem to be as variable in human. But for the other publication, for the other parameters, you know, the 10 or 20% are really just guesses. If you are aware of, when whoever asked that question, when you say that 30% seems to be more typical value for those parameters, if you are aware of the publications that would show that, you know, those parameters should have, you know, closer to 30%, if you could forward to us some suggestions for those references, we'll be happy to change the default values. Again, they were set initially because we had nothing to start with and didn't want to create too much of variability if there is none, but we'll be happy to adjust those if we have any information of what the real variability should be.
Okay, thank you. Does GastroPlus have variability information for genetic population differences, for example, extensive and poor metabolizers for a specific enzyme?
No, not right now. Currently, you would have to really make the modification. One of the aspects is, again, a little difficult to get the actual expression levels. The other aspect is that the extensive poor metabolizers may not be necessarily only the expression level of the enzyme. In some cases, it may be more of a ability of the compound to bind to that enzyme, depending on where the modification is. So you may have to be a little bit more careful about how to incorporate these, but we don't have any built-in genetic variabilities at the moment. Everything is representative more of extensive metabolizers for all of those enzymes.
Thank you, Viera. In the liver impairment models, you mentioned how the paper describes changes in hematocrit and plasma proteins. Is this captured now by default in GastroPlus 9.5? As a follow-up, will this allow us to model plasma protein binding effects for compounds that are binding to albumin, AGP, or red blood cells? Can binding for specific proteins be specified for compounds?
No. So right now, and even looking at these, just so that everybody, where was it? I think I went in the wrong direction. Even though the publications are showing the different concentrations of albumin and alpha-glycoprotein, if you actually look at how much they are changing compared to the baseline value or to the control, the fractional changes or the percent change is about the same. So it's still covered as a total change in the protein level and GFR and so on. We have not implemented yet the differences in binding for individual proteins. We are still dealing with it more as a fraction unbound in the total fraction unbound, which is being scaled based on the percent of the total protein. And again, some justification is that both of those seem to be changing at about the same rate.
And can you confirm that the changes in total plasma protein levels and hematocrit are updated for the different liver impairment models?
Yes.
Okay, thank you. Okay, another question is which DDI standards have been revalidated so far with the new FUT models?
Again, one of those that we started with was Ketoconazole. We are sort of covering, we didn't go through a complete set through many of those. We are sort of taking a broad spectrum of looking at all of those at once rather than going one by one. So that's why for now we are keeping all of those with the version 9.0 FUT calculations until we have everything completed, and then we'll be switching them over. So far, we've been doing at least some of the simulations looking at the Ketoconazole and a couple of other compounds, but some of those were showing differences. Ketoconazole was not showing much difference, but there is still a lot more work to do. So the complete validation wasn't completed for any of those.
Okay, thank you. On slide 25, when you show some of the validation work with Midazolam, can you just repeat what were the changes in the results between version? What was responsible for the changes in the results between version 9 and 9.5? Is there any change in the expression levels of the enzymes in the gut and liver, or is it just all due to the FUT changes?
It is all just due to FUT. As you see, I didn't point it out in great detail with Midazolam, but you will see with version 9.5, the FUT in liver would be estimated at 3%, while in the previous version it was estimated at 8%. Right? So that change in the fraction unbound and in the unbound concentration would cause that previously there was more drug available for the metabolism quickly, so it resulted in slightly higher estimate. But other than that, these simulations are based on using exactly the same models, exactly the same physiology, the same KPs, the same KMV max values. The only change was in the FUTs, and again, the liver FUT would be the major one that would be affecting the elimination of the compound.
Thank you, Viera. For the new log files for the mechanistic deconvolution approach, does that mean that we can reuse the previously estimated or fitted mechanistic deconvolution for generating IVIVCs with a different dissolution method?
For creating IVIVCs, yes, it will be possible to do it, especially due to the process. So one thing is the program will not read back the log file. That's, we didn't take it that far. But the program will, that log file will contain the fitted viable parameters. And what you can do, the same thing as I was showing here for the, in this last step for the CRD files, you would be able to do the same thing, define the viable parameters for the DSD files. So to make faster correlation at the later stages, once you have the deconvoluted in vivo profiles, you could enter your deconvoluted parameters into the viable profile. So the program here uses them as initial estimates if there are viable parameters already in the DSD file. So you could enter those into the DSD file, and then it would run through the deconvolution step much faster. Wouldn't have to do deconvolution. It would quickly reach the equilibrium, and you would go straight to the correlation step. So it's not going to completely eliminate the subsequent deconvolution, but it will give you options to do it much faster.
Thank you, Viera. With the lysosomal trapping case study that you went through, is the adjustment to the fraction unbound and enterocytes implemented in GastroPlus 9.5, or is it a feature that's specific to MembranePlus? And then a second part to that question is, have you considered the lysosomal trapping effects yet on tissue distribution within the PBPK model?
So the first question, the fraction unbound in enterocytes, is actually something that is available already in version 9 and was available ever since version maybe 2. You can enter different fraction unbound in enterocytes. You will have to go through drug stable, and it may be a little difficult to find. I'll show you just very quickly. The fraction unbound in enterocytes, you can see it in the drug stable about here, where you can enter different fraction unbound in enterocytes. So that is a GastroPlus parameter. We used MembranePlus to just estimate what might be the fraction unbound in enterocytes for a compound of specific properties. So MembranePlus is more of a way of predicting it, what it might be, and helping us to predict what that Tmax or what effect it might have on pharmacokinetics before we have in vivo data. When the second part of the question, did we look at it in terms of predicting the distribution? Yes, we don't have more mechanistic way of accounting for it in the distribution. The way we are dealing with it for now is by increasing blood to plasma ratio when calculating the KPs. And just a short story, blood to plasma ratio is used to calculate binding to acidic phospholipids, and it appears that the concentration of acidic phospholipids is higher in the tissues that are known to have higher lysosomal trapping. So calculating the KPs with the higher fraction and with the higher blood to plasma ratio would give you higher volume of distribution, and especially increased in the tissues which do account for where the lysosomal trapping would be higher. It is a similar process, again, was described in this paper that should be available any day now. And I lost the note here, but it's also something that was done for calculating the volume of distribution for methylphenidate. The blood to plasma ratio to calculate KPs was set to higher value to account for that effect. So that part is not so mechanistic right now, but we have workarounds that we can suggest to deal with it.
Thank you, Viera. Regarding the default enzyme and transporters in the program, does GastroPlus 9.5 have any updates to default expression levels in the gut or different tissues of the PBPK models?
The only ones are the ones that we have are related to the Chinese physiology, right? And of course the changes in the expression levels due to the liver cirrhosis, but we sort of ran out of time and were not able to add expression levels for the new species at this time.
Thank you, Viera. Can we customize the iteration parameters for the mechanistic deconvolution inside of the IVIVC plus module similar to the way that it can be done in the optimization module?
No, not right now. Really the only thing that you can do at the moment is to change the objective weighting function, but any other customization is not possible at the moment.
Okay. There's one question that I'll address. It's related to the intramuscular injection models and how they can be accessed by customers. This is a sub-model, I guess you would call it, of the additional dosage routes module. And so there would be a small additional cost associated with licensing it and having access to it. But of course, at any point, we're happy to provide trial licenses to that feature or any other feature so that you can see how well it works with some of the projects that you have. And then there's several questions related to when GastroPlus 9.5 will be available and whether or not, I think more importantly, companies will be able to install 9.5 in parallel to 9.0 and allow users to decide which version to use. So can you comment, Viera, a little bit on the installation of GastroPlus 9.5 and whether users will have the option to decide which version they would want to call up?
Yes, that should not be a problem anymore. Actually, starting with version 9.0, all of the background and system parameters as well as the installation directories are starting to be versioned. So you could have on the same computer, you could have side-by-side version 9 as well as version 9.5. And since they are both using the same licensing system, that will make this possible. So yes, you could have both versions on the same computer. As for the release, I'm almost afraid to say this again because many of you have heard me to say this for last couple of months, that it's about 2 or 3 weeks, and we still keep running into delays. But yeah, hopefully another couple of weeks. We are really down to the final testing and just a few items on the documentation. But we are really trying to finalize it as quickly as possible now.
Okay, thanks, Viera. There are a couple of comments from users on suggestions for improving some of the features with GastroPlus. We'll make sure that the development team receives those and prioritizes them as we get ready for future releases of the program. Otherwise, there are no other questions remaining, so what I'd like to do is now wrap things up. First, very much thank Viera for her time today, giving us a very excellent and insightful overview of the new features in GastroPlus 9.5 and some of the cool things that we're doing with MembranePlus to help us assess the impact of changes to lysosomal trapping. And also, we want to thank everybody who's on the call for staying with us for the last 75 minutes or so. We are going to conclude today's webinar, but as a reminder, if you did miss any part of today's presentation or you would like to share it with some colleagues who couldn't make it, the playback will be available at our website, www.simulations-plus.com. Also, stay tuned for formal announcements of the GastroPlus 9.5 release. At least one, usually multiple representatives at your company will be receiving a notice to go to our online share file portal and retrieve the GastroPlus 9.5 installation package. And also be on the lookout for an invitation to join the GastroPlus user groups webinar that's scheduled for March 28th. It's going to be a continuation of some work that Roche has been doing on modeling the effects of dissolution and precipitation in some very unique ways. So an announcement inviting you to register for that webinar will be coming out within the next couple days. Thanks again, everybody, for taking time to listen and for joining us, and have a very wonderful day.